And we are live. I don't know how many people will actually watch this because this was kind of abrupt, but I kind of wanted to keep going. So, for people who have not watched the first part, um, we've just spent a couple of hours today in the morning kind of working with WebAssembly, um, porting a let me move this stuff here. Porting scalar algorithm to use WebAssembly SIMD instructions. And where we left off was that we have code. The code runs correctly, but the code isn't particularly fast. And so like the issue is we are hitting a combination of issues in the stack where I'm writing some CMD code and I expect the CMD code to map a certain way to the x64 instruction set, but it doesn't for one reason or another. And some of these cases are cases that we can improve. Some of these cases are cases that we can't really improve. We have to file bugs for like V8 engine and then basically see what happens, right? So I thought I'd keep going a bit. I have a few ideas that may or may not work out performance-wise in the sense that, like, given a perfect code generation engine, I think they would improve performance substantially, but we are clearly dealing with some imperfections. So we'll see how this goes. I started filing issues for V8, and we are gonna file like one more based on the bugs that we've discovered. So I just filed an issue where the disassembly instruction wasn't working, right? The disassembly wasn't working, I should say. I just filed, so I looked a bit into this shift stuff, and what I discovered was it looks like shifts actually get compiled into 4 instructions, which might throw some of my plans for optimization off. But here's what happens. Like the compiler, so this is a shift by 16. What should happen is, I just had this open, shift left. Let me, so we are dealing with word shifts, something like that. What did it say? PSLD. So it's like a double word shift. So what I'm expecting to see is I'm expecting to see this instruction generated that takes a vector and then shifts it by the constant that is specified in the instruction, right? So what happens in the V8 instead is something much worse. It loads the constant into the register. Then it masks this register using 31 as the mask, so that if the constant is larger than 31, it gets truncated to the last 5 bits. Then it loads the value into the vector register, and then it uses the vector shift, which maybe this is also slower than the immediate shift, I'm not sure. But like all of this is not great, so we have 4 instructions instead of 1 instruction for each shift. This could also be impacting performance in my other codec. So this is a great find. And there was something else that I wanted to file based on the same blob of code. So let me just file the rest. Yeah, I wanted to file this as well, where there's like an extra mov, which is not clear that it should be here. Redundant register move in plus some CMD code gen. Attach a file. And then what I see is this guy. Oh, actually, this is also broken. There's like a lot of extra mobs here. I'm just gonna copy and paste this in the following sequence. 1, 2, 3, 4. It looks like all 4 mobs. Like they can be eliminated, and instead the following instruction can use the source register directly. So that's what it seems like to me. So that's one more. So, and then there's the final issue, which is this crazy code gen that we kind of stopped, like left at last time. I'm not sure if I should file this, maybe I should. So I wrote a script. The way we're gonna do this is this. So I wrote a script that takes the file that we have, it compiles it using the LLVM into the LLVM assembly, then it compiles it into WASM assembly, and then it compiles this into x64 assembly. So now I can just do this. Oops, well, whatever, build sh. Let me make the font larger. There should be no S here, but it doesn't matter. And then it's gonna update a bunch of stuff. So I want to file, but I might want to file one last issue for V8, but I want to see where kind of it's coming from. So after the square root, so like we are dealing with our presumably fast way to implement the package that I was talking about at the end of part 1, and it looks like it's generating pretty horrible code. So I want to kind of just see why that is, because I didn't expect this. Oh, yes, okay, never mind. Yeah, so what looks like is happening is that either this or this, like somewhere between these two, LLVM generates a bit shuffle instruction, byte shuffle instruction, which, I mean, I didn't ask it to, but of course it's free to do whatever. I'm not sure where it's going with this, but it pretty clearly results in kind of catastrophic code generation, because then the is it present here? Because then the what's it called? V8 engine compiles that pretty poorly. So I should file an issue on that at least. I know what I'm gonna do. Let me kill that for a second. And then I'm gonna leave this, this. And then I have an idea of how to improve all of this stuff a bit, but I wanna file the last V8 bug first. Oh. Interesting. I'm not sure what these shuffles are even doing here, honestly. Like there's one shuffle in my LLVM assembly right now, and there's a lot of them. So this might be a LLVM issue, not a V. I mean, there is a V8 issue for sure. This is odd. Unfortunately, I'm not an expert in in WASM, like stack codes. It's hard for me to read this. I'm not sure exactly what it's doing, but it's doing something stupid. Yeah. Questions about Roblox and WebAssembly. No plans. I don't think it's the right fit for what we're trying to do. So this is interesting. Yeah. Let me look at this again. This might be an LLVM issue, in which case I'm not quite sure where to file that, honestly. And like how to file it in a way that I don't have to keep this code for eternity. So it's doing bit select here. Yeah, something bad is happening here. But it's in the sign handling, which I was... Okay, let's just ignore this for now. I'm gonna rewrite the sign handling because I wanted to do this anyway. And then maybe this thing will disappear or maybe not. We'll see. So one issue that I was encountering, let me revert back to this code, I guess, is that, or maybe to this code, is that the sign handling seems like it's creating a problem for me. So what I want is, roughly speaking, I want to say, hey, if n2 is 0, then I want to use, if each component of n2 is 0, then I want to use the component of in ZF, which is an absolute value of the computed component as is. Otherwise, I want to do this. So it seems like what I wrote should be a reasonable way to do this, but it's not. So let's do something else instead. So minus ZF is equivalent to not ZF plus 1, I think. Yes. Sort of trust me on this. So the thing is, this n2, which is like the sign, it's either 0 or 1. So really this is the same as this, and this is the same as this. Oops. Now, not is the same as a value that's all ones, XOR like another value, and this is the same as this, XOR this. So the upshot of this is this. So like if n2 is either 0 or 1, we can make another value that's either all zeros if n2 is 0, or all ones if n2 is 1. And then we can implement like the other thing, like this branch basically without selects, just by XORing and then adding something. And the other thing is, I'm not sure if it's actually better, but so let's do this. Let's call this ZM or something for mask, and let's do this. So this thing is 0 if n2 is 0, and then -1 effectively if n2 is not 0. So then we can say that instead of doing this bit select, we are gonna do XOR ZM which is like this part. Oh, but sorry, wait, this is wrong, hold on. I guess I need non-equal or something, yeah. So now this thing is 0 if it's 0, and -1 if it's not 0, because it's, yeah, okay. So XOR, and then I was going to try, let me do this, I guess. I can subtract the mask, because plus n2 is the same as minus n2, right? And then if the sign is 1, then the mask is -1, so instead of adding 1, we can subtract -1. So like, I think this is an equivalent code generation, an equivalent like code sequence to the bit select stuff, but it might run into fewer issues because I was looking into bit select, and bit select is like 3 instructions on V8 as well, so maybe this is going to be better somehow, maybe not, I don't know. Oh, right. So let's see. Let me look at the generated code and then we'll see what happens. I'm getting this weird shuffle again. Let's do this. Let's see if this works. Okay, the code works at least. I don't think the code is fast. Something still happens that causes a problem. Alright, so don't understand this. Let's see. So I'm still getting these weird shuffles, but then I'm getting the usual like splat and everything else is fine. So I wonder what's up with that. Maybe I have to implement all of the things that I thought of doing, because it looks like, unfortunately, it looks like, oh, this might be, oh, I know what this is. Is there a widen here? Something? No. Let's see. Widen low high. Let me try to do this because I don't get this. Great. All right. So let me ignore the generated code for now and let me do all of the changes that I wanted to do, because now I'm suspecting that shuffles from here are interfering with this code somehow. And if that's true, I mean, it's gonna be like hard for me to fix this problem before I actually solve this here. The good news is that this code should be better than the code that I had before, regardless. Like in context of perfect code generation, this code should be better. It's just that we keep hitting these stupid shuffles, which I'm not sure where they are coming from. But if we can fix that, then performance should be good. All right. So I was talking in the previous stream about how, you know, like I have 4 things, and they go like this: x, y, x, y, z as 0, and then there's 4 of them, and then I want to transpose this, right? The thing is, I'm kind of doing a lot of work for something that could be implemented in a more efficient way. Here's the full thing that my code from before is doing. So there's this x, y, z, s, 0. These are bytes. And then there's 4 of them, right? But this is all in one vector. So this is v, right? So then what happens next is I do this widen operation where v has 16 bytes. Then first I widen this into 2 vectors with 16-bit integers, so 8 values in each one. Then I widen this into 4 values in each one, right? So I produce 4 vectors. Then I transpose these 4 vectors, and the way that the transpose works is it kind of makes like 4 extra vectors out of the 4 source vectors. And then it mixes these guys into, I think it's like this, basically. Bam, 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 bam. So this is the full sequence of operations that I'm doing. So this is widen to 16 bits. This is widen to 32 bits, and then this is transpose. And so you can see there's a lot of temporary stuff that we are generating, right? There's like many vectors that we have to generate in order for us to actually get to the result that we want. Now in this specific case, we don't have to go through this trouble because our source inputs are kind of packed in bytes. What we can do instead is we can say, well, if you look at our source vector as a vector of 4 32-bit integers, then, well, what happens is there's like 4 of them, and in each one, we have these x, y, z, 0 packed, right? But if we wanted to get, my whiteboard connection terminated somehow. Oh, okay, all right. So if we wanted to get from this vector to the vector that has, say, x, 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 and x, well, we could just move bits around so that everything lands in the right place. And so we need to do sign extension from 8-bit values to like 32-bit values, but it's actually pretty trivial to do with shifts. So I wanted to try to rewrite this code in the front of the loop to use shifts exclusively. Now, I just filed an issue on V8 where a shift is compiled into 4 instructions instead of 1. So this may actually backfire. Like I may implement this and then it'll turn out to be a really bad idea. But I mean, that's the only thing we can do. We can try. If this doesn't work, then I will have to try to fix the shuffle issue in some other way. Let me look at the comments a bit. I'm not going to discuss Linux and Roblox. What's the rationale between writing WASM by semi-hand instead of targeting language to WASM? Well, I'm using C, right, to compile to WASM. So I'm not writing like WASM assembly code by hand. However, I'm using WASM SIMD intrinsics, right? The only other way to get WASM SIMD code is to use compiler auto-vectorization. And this was actually a problem in part 1 where compiler accidentally, or unknowingly, I didn't know that, compiler actually vectorized the code. And we couldn't even run the code that the compiler produced because it used some instructions that V8 doesn't support yet. Plus, I'm not sure what the quality of the vectorization was really. So yeah, there is no real option right now other than using intrinsics manually. Like you could probably use some other library that wraps, like that supports WASM, so that instead of saying WASM mul, you could say A times B. But pretty much it's kind of like the only real option right now. So we don't have a choice. This is off topic a bit. I may come back to this if my code like works or. All right, so let's try to use shift. So what we're gonna do is we're gonna say, well, let's like change the computation strategy that we're using completely. So we have a vector that's like x, y, z, 0, w. So then we want to get three things out of that. One is we want to sign extend x. So we want to get the 32-bit value that is equal to x, considering x is an 8-bit integer. And the way to do this is this. So imagine that you treat this as the as like a 32-bit integer, right? So what it boils down to is, because of the little endian order, it looks like this as a hexadecimal integer. If we shift this to the left by 24, then this gives us 0x, xx, 0, 0, 0, 0, 0, 0. Then if we shift it to the right by 24, but this shift is arithmetic shift or sign shift, right? Then we get effectively 0x, xx if the high bit was 0, or we'll get all f's where if the high bit was 1. And so this is what we want. So this is kind of like sign extension. This is what sign extension looks like. And maybe this will work. I mean, this should work. Maybe it'll be faster. We don't know. So let's try that. So effectively what I'm saying is that instead of doing everything that we were doing before, we'll just say wasm i32 amps for shift left. I'm not sure what the intrinsics are. So there's shift left and then there's shift right. And then shift right has two variants: signed, which is arithmetic, and unsigned, which is logical. We need signed. So shift left and for 24, and then shift right, the result 24. And so this may seem pointless, but again, this does a sign extension. And then the same thing for n1. Oh, well, not quite the same, sorry. For n1, it's we have to shift by 16, because that gives us, basically that shifts yy to the top byte, right? So we have to shift by 16, but then the right shift is still by 24. And so then the final thing we want, or I want, is n2, which is z, which let's for now do the exact same thing, and then we may come back to this. So this eliminates all of the transposes and all of this stuff. Whether it's fast or not, we don't know. I mean, whether it works or not, we also don't know. But that is easy to tell. Let's do this. All right, we are twice as fast as we were. I'm assuming the code still works. All right, cool. I am happy my idea worked. So I suspect that it's not like one idea that worked, it's like two ideas that worked, because let me try to do the obvious thing. Not the obvious, like the more optimized thing that we tried last time. Yeah, and that's much slower because I'm pretty sure this code is hitting this shuffled stuff. Yeah. So let's do this. So note that so this transformation is actually a good transformation regardless, because it's like it's reducing substantially the amount of work that we need to do. So instead of the scary thing that I drew here, where I have to take the value and then make many temporary values, instead what happens is we take the value and then let's draw here, right? And then we compute three values from this value. First is shift left, right, by various amounts. So like that has 4 integers in each one. And then the result, which is a shift right. That's it, right? So instead of, what is it, 12 plus 2, 14, instead of 14 values, we generate 6. Now, let's look at the assembly output. I'm assuming that we are still losing a lot of time due to the shift performance deficiencies. Oh. So this is nice. I'm not sure what this is doing. Oh, it's like reordering things somehow. Alright, so this is actually better than I expected. Let me see. Although, why does it shift by 25 and 2? I don't fully understand this. And then there is some shuffles, and then 26 and 2. This is weird. I would have to read this code thoroughly to understand, cause I didn't expect this, I guess. The code seems to work though. Let me check if the code actually works. What's the best way to do this? We can use, I guess we can use our debug print stuff if that still works. So build that. Let's see, 72, 6E, 77, 75. Yeah, you know, like it seems to work. And we can visually compare the results with the scalar code, which hopefully they're the same. So to get there, we will do this. Let's confirm. Alright, so we are running scalar code here, and oops. Alright, so the results are identical, so that's good. I'll need to study the assembly code because it had a few things I did not expect to see there. But okay, so largely speaking, the approach works. Instead of doing all of these transposes, like we don't even need the transpose function anymore. It's funny, it took me so much time to I had to write this transpose function, and there was a bug in this and stuff like that in part 1, and then we didn't even need that. So that is nice. I can remove this. And let me see. Shift left. I'm trying to see if there is anything else that I could be doing better here. Maybe, but okay. Let me remove all of that for now. I'm not sure I still need this guy, but let's see. Oh, there's a lot of discussion in chat around stuff. Uh, Let me briefly cover the questions. So, yeah, again, not gonna talk about Linux. It's been covered elsewhere to death. What culling and batching algorithms can I recommend for game engine and racing simulator? Forest buildings, huge number of game objects. So, right. So I guess occlusion culling is the most interesting question, right? But like there's a lot of different options for that. I don't know if racing sufficiently constrains the problem to like suggest the optimal one. There are software methods, so I'm not sure I've seen these sparse 3D bitmap generators, but there is definitely an algorithm. Intel has a library. I don't remember what it's called. But Intel has a library that does software occlusion culling. Yeah, this one. Mask software occlusion culling, which is like a very fast rasterizer that uses AVX instructions. Uh, uh, and apparently you cannot export this program to Cuba, Iran, North Korea, Sudan, and Syria. Whatever. So that is pretty good if you want this to be CPU based, right? If you want GPU based solutions, there is a host of solutions using occlusion queries, but for that you have to accept some amount of frame delay, right? Or you can use, it doesn't have to be occlusion queries, there is a presentation called rendering with convection or something like this. Convection. Yeah, about splinter cell convection, which describes a not software, sorry, like it describes a method that is not using occlusion queries, but it rasterizes the depth buffer on the GPU and then creates a coarse representation of the depth buffer, and then in a compute shader, I think, calls the objects against that. And my project Niagara does something similar to this, but without the extra delay, without the extra frame delay. So like that is an option. There are options where you don't use occlusion queries, you use compute shader or something like that, but then you copy the result of the tests in from compute shader to the CPU, and then in a couple of frames you read that. There is also other methods like, so this mask software occlusion culling, it uses a complex rest, right? Complex is not the right term. Like it uses a bit, if as far as I remember, it uses a bitwise rasterizer with some tricks to make it really efficient, etc. And so it's kind of important if you have a lot of geometry in your occlusion data. But if your geometry for the occlusion data is simple, then you don't need to do this. I worked on a sort of software. It was running on SPUs on PlayStation 3 software occlusion system that was similar to, I think, Battlefield SPU occlusion culling. Maybe talks about this or maybe not. Yeah. So similar, I think it was before. Is this 2011? So this was before 2011. So I'm not sure. It was not inspired by this presentation, but I think these methods are all pretty much the same, and I think BF3 did the same thing. And so this is basically a software rasterizer that just rasterizes depth like the usual way and then calls against that. So there's a bunch of different ways to do this, right? Like it's hard to know what the absolute best method is, especially if you can use advanced features of the GPU, then that's probably better because GPUs are better for this kind of stuff. But this may mean that you have to implement various really advanced rendering pipelines like bindless rendering, basically fully GPU driven rendering pipelines, which is good but might not fit your specific hardware. So it's hard to give a general advice. Um, will I ever do a live stream asking? Yeah, maybe. Like, at some point, we might do a live stream where it's just, hey, what features do people want, and I will talk about why they might be hard or easy, or maybe we're already working on them. But this will not be the stream. And this stream has nothing to do with Roblox. Absolutely nothing whatsoever. This stream has everything to do with us getting fast decoding. So, alright, so my idea worked. I'm happy about this. Now I want to know two things. One is, do I still need this like weird workaround or not? And the other one is, what else can I improve? So let's try this first. And then I'm gonna look at the generated code. I didn't fully get the generated code because it had shifts for extra amounts. Like I had a shift to 24 and it shifted by 26. So I'm not quite sure. Okay, so this code is still fast. So that's good. And maybe I can do better than this bit select thingy. But let's see. Let's see what the code is doing now. Oh. There's a lot of it for some reason. Let me see here. Alright. X, Y, Z, S. So I will leave a comment. Sign extends each of x, y, z in x, y, z 0 by with arithmetic shifts. We technically don't need to sign extend z, but we do need to move it someplace. So I'm assuming this is still the best way to do this. Maybe not. Let's see. Yeah, like, I mean, I don't need to. I could keep this guy shifted left. Oh no, I can't. Yeah, I need to do this. Well, there's a sort of hacky way to remove one shift here, but I don't want to do this for now. Alright, so let's look at generated code. Let's look at LLVM is not going to have anything interesting, I guess, but still, let's look at this. The main thing I'm looking for is the lack of weird, like, shuffles and stuff like that. Alright, so this is all super reasonable. Oh, wait. Here's my shift by 2. Oh, shift by 2 is this guy. Wait, why by 2? Shouldn't it? Well, I guess it's fine, yeah. So this is 24 shift left, 24 shift right. And then someplace else, I guess, I would expect to see more shifts. 16 shift left, 24 shift right. Okay, so the WASM code is very, very simple now. It doesn't have any shuffles, which is where my major source of coding issues was, right? So that's good. This means I'm unlikely to hit more of these problems here. Yeah. I should add a comment that branchless it's like n2 minus zf using negative zf equals to not zf well, like -1 XOR ZF -1 identity. That's a cool trick that I've used many times before, which is why I thought about this. Like if you want to conditionally negate a value based on a mask without branches, this is kind of how you do this, where you use XOR to conditionally invert the bits and then add or subtract 1 conditionally again to kind of finish the computation. So what are we looking at? So now we're looking at the real x64 assembly, and I'm gonna try to like see if I can do anything. This is way better than kind of what we started with. To put this in perspective, so the scalar code was running at like 0.4 or something gigabytes a second. This is running at 0.8, but this is not just the function that we wrote. This also includes the actual decoding that is not very fast comparatively. So I suspect, and we're gonna prove that, I suspect that we are running way faster now compared to the scalar version. So the way we're gonna prove that is like this. Let's just compare the time the code runs with the filter, without the filter, and then with the scalar filter. So here the code runs for 15 milliseconds. This is WebAssembly SIMD filter. WebAssembly SIMD filter. Now let's do scalar filter. So this is the code that we started from. So this is running at like 29.4, let's call it, right? I don't want to be like too precise. It doesn't truly matter. Let's even say it was 29 milliseconds. Doesn't matter. So this is scalar filter. Now it's tempting to say, well, CMD makes this function twice as fast, which is not quite true. CMD makes the entire process twice as fast. But the question is, what's the cost of just the filter? And so to measure the cost of just the filter, we're just not going to do the filter. And this is going to measure the baseline cost, right? And then we are going to subtract that, and things will be good. So our baseline is like roughly 10 milliseconds, right? No filter. So this means that WebAssembly SIMD filter is roughly speaking 5 milliseconds. Again, numbers are approximate. WebAssembly scalar filter is roughly 20 milliseconds, right? Like 19 milliseconds. So this is almost 4 times speed up, which is reasonable, right? We are taking code that doesn't use SIMD and converting this to use 4-wide SIMD. So this actually means that we are doing pretty good. I want to see if we can push this a bit further, because more performance is good. And I was worried when adding this thing that it's gonna substantially slow down the decoding process. Looks like with a good SIMD implementation, it's it's not the case. Like the performance is reasonable, but if it can be better, that's good. If it can't be better, then that's what it is. So let's look at the generated assembly. I'm gonna annotate it as I go. I did something very similar in the beginning of the last stream. So I'm gonna only keep the loop. This is the loop. And then I already remarked on this, but so V8 inserts some stubs that call some external function, and I'm assuming that this is a path that we are never hitting because it's like some fallback for something like maybe to generate some error. It would be nice if we didn't have to do that, but I'm guessing either it has to do this or it hasn't been like optimized out yet. So we're gonna kill that to just make the code more readable. All right, that's our code. So this stuff I think is like loop prologues or something like that. I don't exactly know. There's like 3 comparisons here, and then 1 comparison at the very end. I was kind of hoping, like I would have hoped that we don't need like 4 comparisons in the loop. We only need 1, but maybe Chrome needs to do something that I'm not thinking of, so it's fine. So then let's look at this. So we load the value, then we do a bunch of work. This is like I talked about this already. These 4 instructions are one shift. One shift. Oops. I think RDI was 16, so I'm assuming it's like shift left by something. I'm not actually sure it's 16, but shift left by something, right? Then this is one more shift left. And this is one more shift. Wait, no, hold on. This is shift right. So this is where, like, if V8 was better at doing code gen for this stuff, which I'm hoping it can be, I filed a bug on this, right? I can add, I'm gonna add my newer code here as well, because here the difference is like more pronounced. So this is one more shift right. There should be one more somewhere, because I have like 3 shifts left and then 3 shifts right. So there should be one more of these guys. There isn't. I'm not sure why there isn't. Maybe LLVM optimizes the thing that I was, whatever. So if you can see now, this is substantial, right? So like my entire loop is what, like 75 instructions or so, executed instructions, and then like 1, 2, 3. Wait, where is one more shift left? It's doing something funky with this value. I just know this. I should do the same thing that it's doing better. Here are some more shifts. No, this is different. Oh, here's one more left shift. No, this is this one. Okay, I'm not. I need to think about this guy. I think it just did. Whatever. But point being, so let's say 75 instructions, and at least there's 4 shifts here and 3 instructions in each, so at least 12 instructions are just wasted doing nothing useful. And this could be a large impact, right? Because like 12 out of 75, if you assume each instruction is 1 cycle, etc., which may be wrong, it's pretty substantial. So then this is integer to float, multiplication. I filed a bug about this. There's many extra mofs here that probably aren't warranted. So this stuff, square root, multiply. Okay, this is where I stop understanding the code. Let's look at this again. So this is the square root. So after the square root, we multiply the result of the square root by something. This presumably is the multiplied by 127. Then we need to add 0.5. And this is where we add 0.5. There's also some comparison. Oh yes, so this is right. So this is the transformation that the compiler is doing here, which I thought of just now, and it's a good transformation. What the compiler is doing is saying, well, the only place where the sign is used, which is this z, right, is in this comparison, where we compare it with 0. So what we are doing is we are saying, let's compare the z value in this vector to 0. But instead of doing shifts and things like that, we can instead say, well, let's end this with 0, 0, minus 1, 0, which will give us 0, 0, z, 0. And let's compare that to 0 instead, because that's gonna be the same. So that's a good transformation. I like the idea. And I'm gonna just implement the exact same thing just to make it more obvious that this is like going on, and to make, I like it when the mapping, when I'm writing intrinsics code, when the mapping between intrinsic code and the kind of compiled result is close to one. So this seems like a good, and this seems unambiguously good to do, like regardless of, well, except if constant loads are slow. If Chrome had fast shifts, this could be not that good of an idea, I suppose. It's probably fine. Oh, is this the same mask? It's the same mask here. So really, this is like z bits or something. And so this presumably is just as fast, but now I understand what's going on better. Yep. Oh, and my beautiful assembly annotation kind of went away. Right, so this thing is kind of odd. Oh yeah, so I think I'm pretty sure that what happens in the rest of this function is that when I truncate, when I convert from like floating point to integers, I'm pretty sure that as usual, instead of just emitting one instruction, the compiler emits like a bunch. Not the compiler, the V8 code gen. Let's try to confirm this theory. Yeah. So there's a conversion instruction, but then there is a jump. No, this is not the vector one. So this, I think, is what I'm using. I'm using conversion from the floating point to integer, and as you can see, there's a lot of stuff here. And this is exactly, yeah, I'm seeing shifts by 31 and stuff like that. I can't do anything about this. That's the only way that I have to convert from floating point to integers. I don't actually care about what happens to nans and stuff like that, and negative zeros and whatnot. So this is unfortunate. So this is an issue in the spec, just like there was an issue in the spec with max instruction. This is an issue in the spec where there is one instruction that can perform floating point to integer conversion, and the specific behavior of that conversion for nans and stuff like this may not be portable, but I don't care. Like, I will never see nans in my code in this code path. And so I'm paying for this with 1, 2, 3, 4, 5, 6, 7 extra instructions. So that seems like an issue that I should file on the spec, because that's the way WASM SIMD is designed. Is like you have a thing you need to do, you try to find a reasonably cross-platform way to do the thing, but if you can't do that, they usually standardize something that works exactly the same across all platforms, but this means on some platforms there is a large performance impact. And so here there's a large performance impact, right? So this thing cost me 7 instructions out of roughly 75 instruction loop. So that could be 10% of my entire loop doing nothing useful. Not good. Nothing I can do about this now. Apart from that, everything else seems fine. So I think effectively there are 2 issues here. Sort of 3. There are 3 issues here. So one is the extra mobs. I filed an issue on that somewhere here. It's a slightly different. It's the same basically instruction blocks. It's the same issue. This probably can be easily fixed in V8, I'm guessing. So the other issue is this shift by constant thingy that costs me again like 12 instructions easily or something. Maybe even more. I'm hoping this can be fixed. If it can be fixed, I'm expecting this to substantially improve performance, like noticeably improve performance. But I don't know, this might be a more involved change. Maybe I should file an issue on the spec here as well, because the big problem here is that WASM doesn't have an instruction that shifts by an immediate value, and so the V8 engine has to trace the values kind of through the rest of the code to understand that it's actually a constant. And the final issue is with this thing that I have just discovered with floating point integer. So I think if all of these get fixed, I feel like the thing could be like 20% faster or even more. But as it stands, it's not too bad. Like, it drops performance from 1.2 gigabytes a second to like 0.8 gigabytes a second on decoding data. It's basically fast enough. It would be nice if it were faster. Like it would be nice if it was basically zero cost. Like you just use it, you don't worry about a thing. Here it's not quite zero cost, right? It has a cost. Oh, one other thing I wanted to check. So let me see if there's anything in chat. Oh my god, there's a lot of discussion in chat. I will read this later. So the filter is called from decode vertex buffer. Like I had to change the API for decode vertex buffer to call filter in small chunks. This is because I was worried about the cache efficiency of this code. Cause like I was thinking, well, this code is probably memory bound, so it's probably a good idea to make sure everything is in the L2 cache. Maybe even L1. I don't know if that's actually important here, given the performance numbers that we are seeing. So let's just, out of curiosity, and I can clean up the code because I don't need debug prints and stuff like that. And also I will need to now think, so now that this code works and is pretty fast, so merge Z R into the correct byte location in the output. I will need to write a version of this that handles 3 components, which is going to be pretty simple. It's the same stuff. And I'm going to have to write a version that works with 16-bit values, which is going to be slightly more involved because I need to load more values. And I'm not sure how that's gonna work yet. I'm also not sure if I need this guy to be here or if it can just be like this. Okay. So I need to file a spec issue. What else do I need? Maybe I can file two issues. Doesn't matter. Debug count. What did I want to do? Oh, right. I wanted to see if using the filters separately is actually reasonably fast as well. So, the way this is gonna work is this. So one option, which is what we're doing right now, is to just call decode and pass it the filter function as a callback, and it'll call this function many times during decoding of the data. The other option is to call this thing without the filter, and then if the filter is defined, just call the filter after this. And we'll need some error handling or something, I don't know. But this is the idea. The filter has the following signature, so it accepts the buffer and the vertex count and the vertex size. So TP count size, and I'm just wondering which one is faster. So this is 840 megabytes a second. Filter is not a function, it says. What? What is it? Oh, it's a function pointer. Oh, damn it. Okay then. It's not a great idea, but like unfortunately, generally speaking, WebAssembly is integrated into the JavaScript environment in a really straightforward fashion. Like if you have a thing if you have a function, you want to call the function, just call the function with arguments. Pointers are just integers, which are offsets into the heap, things like that. Function pointers are funky in WebAssembly because it has to be safe, so you can't say, oh yeah, function pointer is just a pointer into the native code, because then what happens if you change this pointer to point into something that's not native code? So because of this, things are a bit weird. And so this is not a great way to do this, but for now I'm just gonna, I just want to measure the cost, honestly. Oops, what? Okay. Call filter. And so then here I'm gonna say instance exports meshopt call filter. Because if I don't have to pass this as a callback, then maybe my API could be simpler. I'd need to... It's not clear if this is just noise. It might be just noise. It looks like it's running at the same performance. Okay. So maybe I'll change the API to not have to do this, like to not use function pointers at all, because this was bothering me a bit. Like it makes sense to use a function pointer, but also if I don't have to use a function pointer, I don't want to use a function pointer. Okay, all right. So actually, it's basically what I wanted to do. The stream is like what, an hour in, an hour 10 minutes. So that's good. Next time I might need to plan a bit better ahead, because honestly, effectively, if I had the like if I started thinking about the shuffles and things like that from the get-go, I probably would have arrived at this solution a bit faster, and then I would have saved some time, not having to deal with like various code generation issues. So that's a lesson for the future. This bit select business is also, by the way, not great. I think bit select is like 3 or 4 instructions right now in V8 output, and I thought it can use the blending function, but it can't, because it's specified to work on the bit level, not the byte level. And blends, apparently, at least the blends that I found, work on bytes and stuff. Let's see. This is different. This is different. I need blend V. Yeah, so like the only efficient way to combine the two values using a mask that's a vector in SSE is this guy. And this guy blends bytes, and so it looks at the byte values. Like it can't, you can't say, oh hey, I want this bit from this value and that bit from the other value. And so this is what would have been sufficient for me, but WASM doesn't have that. So this needs like byte select or something like that. Yeah, maybe I should file that as well. I don't know. Other than that, the code gen is okay. Like I feel like if V8 fixes the 2 issues that I found, this can be 10% faster without me changing anything. And then if somehow the integer floating point conversion can get better, then again things could be 10% more faster, right? And that would probably put us at close to 1 gigabyte a second again, which would be good. All right, let me read the chat. Yeah, so if you want to force inline, there's just an attribute that you can declare like this, and it's called always inline. So generally speaking, in code that's really highly performance sensitive, you may want to use this, especially on your longer functions, because the compiler heuristics aren't always appropriate. But of course, you should always measure. But yeah, it's pretty easy. You can use this, and also there is, I think it's like inline never or something like that, and that disables inlining. Or is it inline always and no inline instead? I mix them up. Maybe it's no inline and inline always. Oh no, always inline and no inline, yeah. So yeah, that's how you do this. This attribute is really useful, obviously, for tuning code, for performance. And in general, you should also prefer static functions, right? Because for static functions, the inlining criteria is a bit different. So they are inlined automatically a bit more frequently. All right, so now we are basically done. Let me file So this is all good. This should be fixable, honestly. Basically, the issues that I don't know that they can be solved are as follows. One minor thing is this issue could be very easy to solve if there was a separate opcode for this, but I don't know if this is the sufficiently motivating example. There was actually, I think in this issue we were discussing stuff. Let me see. Oh, okay. So I have like 5 shifts now, because I have 2 left shifts here, 2 right shifts here, and also I'm using a left shift here to kind of move the value back into the right place. 5 shifts. 5 32-bit shifts by a constant. As a result, V8 generates, so it's like 4, basically 20 instructions to manage the shifts instead of 5. My loop is like 75 instructions long, so that's a large part of the so I mean, I don't know, like I'm assuming so that's one problem, right? So that's the general challenge with WASM I find, definitely with CMD WASM. Like CMD WASM has to be cross-platform because you write it once and then it runs anywhere. But then when you're writing CMD code, you almost always specialize your code for the target hardware to use special instructions and things like that. And it seems like the gains are minute. It's like, oh yeah, there's like one instruction here and one cycle here and stuff like that. But these gains accumulate, and so usually you end up saving quite a bit with like careful tuning for the target CMD ISA, which WASM doesn't let you do, which is like it has to be like this, but because of this WASM CMD is kind of fundamentally performance inhibited, right, compared to the optimal CMD code. Even if you disregard like WASM CMD can only do 4 wide and you can do 16 wide stuff with AVX 512 now. So even outside of that, there is a large penalty. If that's not the case, is it worth discussing an extra series of shift instructions with immediate operands? So large increase of the instruction space. We'll need, I think there's like other 64-bit shifts. I think there might be, where's my spec? SHL. Yeah, there are 64, so there's 4 left shifts and 8 right shifts. So that's plus 12. 12 additional instructions. Not sure if it's worthwhile. If the engines can perform constant analysis. Alright, so that takes care of that. now I need to file this conversion issue. Like, I don't know what to do about this. Like, I don't have a proposal. But I don't like this. Bam, ba, bam, ba, bam. X64 code gen for float in truncation. So, unfortunately, x64 code gen, at least as employed by V8, for the instruction trunsat. Let me see if the yeah, both signed and unsigned versions are like terrible. The unsigned is more terrible. So at least the signed one is like less bad. Yeah. For this guy is really slow. Well, it's really elaborate. Let's put it this way. So this is 1, 2, 3, 4, 5, 6, 7. 7. Yeah. This is 7 instructions for what could be one instruction in x64 if non-handling or overflow behavior didn't have to be specified one. Is there any way this can be improved? I don't have a specific suggestion, but this costs 10% of instructions. Sure how to measure cycle impact accurately on my benchmark, like on my one of my functions. It's even more than 10% if the shift issue can be fixed. Like if the shift issue was fixed, there was also the prologue of the loop that was kind of bad, but if the shift issue was fixed, my loop would be like 65 instructions or so. And I don't know, yeah, it's actually 10%. So it's pretty accurate. Okay. And that's pretty much it. The only other thing is this bit select stuff, but maybe it's not worth fighting for. Bit select is like 4 instructions. Whatever. Alright, so that's basically all I had. To summarize, we have concluded the part 1 earlier today with like vectorized implementation that was barely faster than the scalar implementation, and we have bridged the gap and made it faster, appreciably faster, using a slightly different implementation approach, which ended up being better. It's still somewhat substantial cost, but it's actually pretty close to, like, if a few issues in V8 get fixed, then I will be pretty happy with the whole thing. And we looked at a bunch of assembly, which is always fun. Now that I know that the assembly output works, I can probably take a look at the other CMD code that I was writing earlier. Maybe there are some issues there that I can fix as well. Maybe not. I don't know. Hard to know. And I'd have to duplicate all of this 4 times so that so that my other the 8-byte stuff is gonna be weird. Anyway, whatever. Are there any questions alongside, like, are there any reasonably on topic questions on WASM, CMD, optimizations, and stuff like that? If not, we'll end in like 5 minutes because I didn't really have anything else. One reason why I'm hoping that I can find some more kind of ways to optimize this is kind of stupid, but all of the decoders here, as you can see, they run at more than 1 gigabyte a second, and that's kind of the bar that I've set for myself. Like, okay, if it's at 1 gigabyte a second or better, it's pretty good. I don't have to worry about this further. So even after optimizations, we are slightly below that. With better V8 code gen, it probably can be like 1 plus, but right now it's not. And I guess I don't really need this thing to be a callback, which is nice. So I'll probably fix my code to make it cleaner later. So any questions before we sign off? Did I forget to? Yeah, it's all good. Okay. All right. No questions then. Thank you for joining me. This was slightly abrupt, but I just didn't want to finish. I didn't want to keep the part 1 hanging with the unoptimized code that we have ended up with. Now I actually feel pretty good about this, and this is basically production ready, except that I have to implement other variants of this function elsewhere, like all of these things. But this should be straightforward because it's the same approach, it's the same pattern, just need to fix the constants here and there. Alright, thank you, and see you next time, whatever the next time or thing I'm gonna stream about is gonna be. I'm not sure when it's gonna happen, because when I have something to stream about, and then when I feel like streaming, that's when the next stream is gonna be. Alright, bye.